So now we can get into the good stuff. We're going to find the volume of this cone now, a 3D shape. There's also a pretty easy formula to calculate this area as well. Pi r squared h over 3. So if you're looking to confirm what your definite integral that we want as a result is correct, you can use that formula to go back and check. So to create a definite integral, we need a Riemann sum. And to create that Riemann sum, we need something to sum up. So what we're going to sum up are disc-shaped slices in this case. So a slice look a little something like this. Dotted lines are a little, but this drawing is the outside of the cone, but this slice is actually going to be completely cut all the way through. So we're looking for the volume of this slice here. We're looking for the volume of this slice here. So now it is time for us to get a little creative. So what we need to do is multiply the area of the face of the disk by delta y here to find the volume. So to find the area of the face, use similar triangles. This slice is at a height y. It's an unknown height and has an unknown radius r. That would be the height and radius of the bottom face of the corresponding similar cone to the entire thing, while our big cone here has a radius. It has a radius of 2 centimeters and a height of 5 centimeters. So we can use proportions, similar triangles, to be able to find the area of the face of that disk in terms that we need it to be. So first things first, the volume of this disk is going to be equal to pi r squared delta y. Pi r squared is the area of the face, delta y is the thickness, and that's going to be the volume that we need. So now we can just get the area of the face in terms of y using the similar triangles, because r to y is equal to 2 to 5. So r equals 2/5 y. This expression, 2/5 y, we can substitute that into r of the original volume expression, which is going to give us pi times 2/5 y squared delta y. Simplify that out a little more. 4/25 y squared delta y. The Riemann sum is going to be the sum of all of these disks. So instead what we have going on is the sum of all of these. And now we can let delta y go to 0, and we evaluate from we evaluate the definite integral from the lowest height to the highest. This is going to be from here, a height of 0, to here, a height of 5. So the integral is calculated from 0 to 5 of 4 pi times over 25, 4 pi over 25 y squared dy. You can evaluate this using basic integration techniques, a little bit of magic, and you wind up with your answer. And there you have it. Okay, so our third example is going to be this hemisphere of radius 5. This is another example of something that can be easily calculated using another formula, which is the volume of a sphere divided by 2. Volume of a sphere being 4/3 pi r cubed. So if anything, you can use that as a check to make sure that you've got this in terms of being able to come up with the definite integral as you need to. So I'm going to show you what a slice in this case is going to look like. The way we slice is as such. There are definitely other ways that it can be sliced. But that's it. So yes, this slice, again, in this case, is going to have a thickness of delta y, and the volume of this slice, pi r squared delta y. So now we just have to get r in terms of y so that we can sum up these disks and create a definite integral. In this case, however, we don't have similar cones, so what we can do is use some trigonometry and the Pythagorean theorem to figure out what r is going to be in terms of y. So because this is a hemisphere, from the center of this sphere to any point on the outside, on the perimeter of the sphere, is going to be 5 millimeters in length. From here to our disk is 5 millimeters. We have our height of the disk, which is y, and our radius of our disk, not the hemisphere, but our disk, is r. This forms a right triangle, and we have that r squared plus y squared is equal to 5 millimeters squared. We're going to get this in terms of y, so r squared is equal to 25 minus y squared. Take the square root of both sides. R is equal to the square root of 25 minus y squared. And now we substitute this expression for r back into the volume expression. So we have the volume now equals pi times r squared, which is just going to be 25 minus y squared. The Riemann sum that represents the sum of the volumes of all of the disks from our lowest height to our highest height is going to be this Riemann sum right here. 25 minus y squared delta y. And as we let delta y go to 0, we get our definite integral. We're going to evaluate this from height 0 to height 5, and that's going to give us 0 to 5 pi times 25 minus y squared dy, and that equals our answer.